Hi, I'm Dr. Jonaki Ghosh, faculty at the Department of Elementary Education, Lady Shri College for Women, where I teach courses on mathematics education. In this video session, I'll be talking to you about algebraic thinking. In fact, this is the continuation of a previous session where I'll be again talking about different aspects of algebraic thinking. And throughout this presentation, I'll be using PowerPoint slides. I request you to bear with me while I prepare. So in this session, we'll be discussing about the various processes involved in the learning of algebra, the importance of understanding literal symbols in algebraic thinking, the functional approach to algebra and algebraic thinking, learning algebra through multiple representation, and finally, the theory of reification. So let's talk about understanding algebraic procedures. Much of the algebra taught at school deals with interpreting and simplifying expressions, working with symbols, finding the unknown number or quantity by solving equations, and so on. So, the much of school algebra is actually quite procedural. The role of letters and symbols is considered central to the development of algebraic thinking, and much time is spent on developing students' skill in manipulating algebraic symbols, and a lot of time, in fact, is spent in practicing these kind of manipulations. And the concept of functions and relational thinking, which is actually a very important aspect of algebraic thinking, are often postponed for a much later stage in the school years. Now let's look at some of the processes in algebraic thinking. The first one could be interpreted as doing and undoing. So constantly, one has to apply a procedure and also do it in the reverse. Let's take an example. Polynomial multiplication and factoring a polynomial. So children in the middle school years are expected to develop the facility to multiply two linear polynomials to get a quadratic expression. And at the same time, they should be able to factor a quadratic expression and arrive at these linear factors. Later in school years, they are also expected to solve cubic equations of this kind, x cubed minus 6x squared plus 11x minus 6 equal to 0. So if one were to solve this equation, they would get three roots or solutions, that is x is equal to 1, 2, or 3. So factoring this cubic actually gives three linear factors, x minus 1, x minus 2, and x minus 3. The other aspect is to the reverse process is actually to verify that x equal to 1, 2, 3 are actually solutions to this cubic equation by substituting and seeing that it satisfies this equation. So constantly there is an aspect of doing a certain procedure and doing it in the reverse, that is undoing it. Another important process in algebraic thinking is building rules to represent functions, or writing rules which describe the relationship between two variables which represent two different quantities. Let us have a look at this table where there are two variables x and y. X is the free or the independent variable and y depends upon x. And suppose students are given this kind of a data, they have to actually write the relation between x and y as y is equal to 3 times x plus 1. So abstracting the relation that the y value is 1 more than 3 times the corresponding value of x in each case is something that the student is expected to do, and they are expected to write this relation as y is equal to 3x plus 1. The third process in algebraic thinking is abstracting from computation. That is thinking about computation in the abstract and not in terms of particular numbers. So suppose a student is given the sequence 3, 7, 15, and 31. Being able to abstract the pattern that each number is 1 less than the corresponding power of 2 and writing it the nth term as 2 raised to the power n minus 1 would be referred to as abstracting from computation. Further, in the primary years, they learn about long division of whole numbers, and later on in around grade 9, they learn about the long division of polynomials. And finding similarities between these algorithms is also something which we can refer to as abstracting from computation. Understanding symbols is again something very important and key to developing algebraic thinking. So, understanding literal symbols. Zalman Usiskin, in his 1988 paper, talked about this and emphasized that understanding the meanings of the letters used in expressions is crucial in understanding algebra. Now, students are often confused between the terms variable, parameter, constant, unknown, or formula, equation, identity, and property. So, in his paper, Usiskin describes and lists out these 5 examples where A is equal to L into W may be referred to as the formula for the area of a rectangle. 40 is equal to 5x is an equation where x is an unknown whose value is to be found. Sin x is equal to cos x into tan x is referred to as an identity. 1 is equal to n multiplied by 1 upon n is a property. And y is equal to kx is again an equation where k is a constant and x and y are variables. So all these are examples of equations, but the contexts are different. The first one is a formula. The second one is an equation in which x is an unknown. The third one is a trigonometric identity. The fourth one is a property. And the fifth one is again an equation where k is a constant. So engaging with these various different literal symbols and their meanings is something that evolves with time. And a lot of time has to be spent in showing students the meaning of these symbols and giving them more and more practice in understanding such relations. Among algebraic procedures, equality is perhaps one of the most difficult aspects of learning mathematics. And you might be surprised that it is being mentioned here. But the fact is that equality is something children encounter very early in their primary years. So when they encounter mathematical sentences like 3 plus 5 is equal to 8, they read it as 3 and 5 makes 8. So constant of making or adding up to or totaling doesn't necessarily highlight the idea of an equivalence. So in arithmetic, when students interpret the equals to symbol as an instruction for doing an operation. So if they see 3 plus 5 is equal to dash, they think they understand the equal to symbol as a prompt to do the process of addition. In algebra, the equal to sign represents equivalence. That is, what is written on one side of the equal to sign is the same as what is written on the other in value. Confusion occurs when they encounter equations of this kind, a plus b is equal to c. They don't see it as an equivalence and wonder what they need to do. So this prompt, earlier they thought of the equal to as a prompt to do an arithmetic operation, kind of confuses them at this stage where they're expected to look at the equal to sign as an equivalence. So the balanced model of equality has been propounded as a very important representation of explaining the concept of equivalence. So the idea of a weighing balance may be used to highlight this idea and help students perhaps develop a relational view of the equal to sign. So in early activities with children, the balance model, for example, this picture here shows that, a hen is equivalent or has the same weight as 2 squirrels, and one squirrel has the same weight as that of 8 eggs. So the question being asked is, one hen will be equivalent to how many eggs? So this kind of a task, simple task, requires proportional thinking. And if children are exposed to such tasks, they could understand the equal to symbol more as an equivalence rather than in solving something or applying an arithmetic operation. So the balanced model of equality is a popular analogy which is used, or metaphor which is used for explaining the concept of the equal to sign. Now we would like to discuss the aspect of multiple representations. Being able to see relationships between numbers is crucial for developing relational thinking, which is a critical aspect of algebraic thinking. In recent years, the learning of algebra emphasizes an approach where the focus is on identifying and describing patterns and relationships among numbers. This approach is often referred to as the function-based approach to algebra. So let us elaborate a little more on this function-based approach to algebra. It emphasizes the use of functions from everyday life as the central objects of study in the curriculum. So using this approach, students may be familiarized with a variety of situations in which values of one quantity depends on another quantity. So for example, let's say the temperature recorded at different times in a day. So here temperature is a function of the time, or it depends upon the time of the day. The number of kilometers traveled in a taxi and the overall cost of the trip. So the cost of the travel depends upon the distance traveled or the number of kilometers covered by the taxi. The cost of buying cloth at the rate of rupees 65 rupees per meter. So this again, the cost of buying some dress material, for example, is dependent on the number of meters of cloth which have been purchased. So in each case, there are two quantities which depend upon each other. Making observations from data may help students to see how two quantities, such as in the examples which I just showed you, temperature and time, or distance traveled and cost, etc., are related to each other. Based on their observations, they could be encouraged to find a rule to describe the relationship between two quantities. So the emphasis must be to abstract the relationship between the two quantities and to describe it in some way using variables. To understand this better, let us see the following example. The table below gives the exchange rate of US dollars and Indian rupees, well, as of 8th May 2020. So the first row gives the value of US dollars and the second that of Indian rupees. And you can see there are certain question marks which have to be filled up. So based on the information in this table, we can ask the question, find the value of 3 US dollars or 5 US dollars in rupees or 12 US dollars, or the approximate, or the reverse question, the approximate number of US dollars for 1511.36 rupees. So here, the student has to clearly relate each case, the number of US dollars to the amount or value of Indian rupees. Now, to abstract this relationship between the value of the US dollar and the Indian rupees, we need to make the following observations. First, that 1 USD is approximately equal to 75.57 rupees. The values in the second row of the table reveal that the difference in the rupee values is 75.57 for every increase of 1 US dollar. Thus, to get the equivalent number of 5 US dollars, one may simply add 75.57 to the previous number in the table, which is 302.27. So I'm going to go back to the previous slide. So for 5 US dollars, I need to add 75.57 to this 302.27. And I keep on adding 75.57. And this entails additive thinking because I'm only looking at the row of values for the Indian rupees. The number of rupees may also be obtained by multiplying the corresponding number of US dollars by 75.57. This approach uses a relationship between two quantities, that is the number of US dollars and the number of rupees, and this requires multiplicative thinking because now you're looking at both together. So functional thinking is another form of generalization. In the previous part of this algebraic thinking video, we talked about generalization by analogy and generalization by extension. Functional thinking is another kind of generalization by extension. A function is a relation between two sets of data such that each element of a set is associated with a unique element of another set. Working with visual patterns such as tiles, pictures, etc., offers young students opportunities to think about relationships between quantities that go beyond calculations and arithmetic. So to develop algebraic thinking, the student needs to work with multiple representations of functions, that is pictorial, numerical or tabular, graphic and symbolic, and should be able to transition between these different modes of representation with flexibility. Now let us see an example again. So here is a matchstick problem. How can this example be used to develop algebraic thinking using multiple representations? So this is a growing pattern. So a square is formed with 4 matchsticks, and at the next stage 3 matchsticks have been added and 2 squares are formed. Further, another 3 matchsticks have been added and 3 squares are formed, and this kind of growing pattern of squares can continue. So if we have to represent this using a tabular representation, we mark the number of stages of this pattern as 1, 2, 3, and so on, and its stage being represented by the variable n. We find that the number of squares is the same as the stage number. So the first stage has 1 square, second stage has 2 squares, third stage has 3 squares, and so on. So the nth stage will also have n squares. But the number of matchsticks for the first stage is 4. For the second stage is 4 plus 3, that is 7. Then 7 plus 3, which is 10, and so on. And we observe that the number of matchsticks is actually 1 more than 3 times the number of squares. So this relational understanding is actually reinforced through this tabular representation. We can also represent this data graphically by representing the number of squares on the x-axis. So in this graph, the number of squares are represented on the x-axis, and the number of matchsticks used are represented on the y-axis. So the first square requires 4 matchsticks, the second square requires 7 matchsticks, and so on. And these are represented as ordered pairs 1, 4, 2, 7, 3, 10, and so on. All these points now lie on a straight line. And the equation of this straight line, that is the relation between x and the variables x and y, is y is equal to 3x plus 1. So y is equal to 3x plus 1 is a linear representation. This is the graphical representation, this is a symbolic representation. And in the previous slide, we saw the tabular representation. So all these modes of representation together expressing the same idea reinforces the idea much better. In the previous presentation, we had seen the interesting Sierpinski triangle representation, where at every stage, we start with an equilateral triangle, join the midpoints of the 3 sides and remove the middle triangle. So we get a triangular hole, the white portion has been removed. So we have 3 smaller black triangles, and this recursive process is repeated on each of these 3 triangles to obtain 9 smaller triangles. And thereafter, at stage 3, so this is stage 0, stage 1, stage 2, stage 3, there are 27 small triangles. Now this is the pictorial representation of the Sierpinski triangle construction. But clearly it is difficult to do this construction beyond stages 3 or beyond stage 4, unless there is, of course, a computer program which generates this. But by hand, it would be difficult to go beyond stage 3 or 4. A spreadsheet can be created where we can easily write the stage numbers on one column, the number of shaded triangles, which are actually powers of 3. So stage 0 has 1 triangle, stage 2 has 3 triangles, stage 3 has 9 triangles, stage 2 has 9 triangles, stage 3 has 27 triangles, and so on. And if we extend this, we find that at stage n, there are a large number of black triangles, that is 3 raised to the power n, or 59,049. And the shaded area, if we start with the shaded area at stage 0 as 1 square unit, then at subsequent stages, at stage 1, it is 0.75 or 3 upon 4. And these are all powers of 3 upon 4, as we saw in our previous video session. Now, the number of shaded triangles increases very quickly, whereas the shaded area approaches 0 very quickly. And this idea can be seen in the graphical representations. The shaded triangles are increasing and the shaded area is approaching 0. Finally, we can actually write recursive and explicit rules for the number of shaded triangles. So if T of n represents the number of shaded triangles, then T of n is 3 raised to the power n, and the shaded area is 3 by 4 raised to the power n. We can also express the number of shaded triangle at any stage n in terms of the previous stage by writing T of n is 3 times Tn minus 1. So in this one slide, we see the 4 different representations: the pictorial representation, the numerical representation, the graphical representation, and the symbolic representation in the form of recursive and explicit rules. All these together help to understand the concept better. And no one mode of representation should be privileged over the other. Now we come to the theory of reification, which was put forward by Anna Svard and Linczewski in 1994. They referred to the psychological process of reification and said that it occurs when students transition from viewing algebraic objects such as functions as processes to viewing them as objects. So students initially see these algebraic objects as processes, and later on they transition to seeing them as objects. So this transition from a process-oriented view to an object-oriented view is actually what reification is. Now, in the process-oriented view, the student interprets the linear function y is equal to 3x plus 1 as a procedure to be performed. So when they see such an equation, they feel that they have to substitute a given value of x in this equation to obtain a certain value of y. So they're looking at this expression y is equal to 3x plus 1 as a procedure to be done. But when they transition to an object-oriented view, the student would interpret this expression as a single entity or an object having its own characteristics. So looking at the expression itself, it would immediately register on them that this is a linear equation which is represented by a straight line and which has a positive slope. But this transition takes a lot of effort. And according to Anna Svard, if you teach using multiple representations, that is pictorial, numeric, symbolic, and graphic, children can achieve reification much faster. So to summarize this session, first we talked about understanding algebraic procedures. Then we saw the role of literal symbols and their importance in developing algebraic thinking. We talked about the different modes of representation of concepts in algebra and how using all these modes would help to achieve reification faster. And teaching algebra using multiple representations fosters functional thinking and thus in turn leads to better algebraic thinking. Finally, I would like to end with these references. Thank you very much for such a patient listening. I do hope you found this video useful. Thank you.